Yeah, I'll try and keep this as high level as possible so that it's accessible. So I probably won't dwell too much on some of the algorithmic details. But if you have any questions about those, feel free to ask at the end. Um, so I guess like essentially what we were doing in this project was applying methods that were developed to handle problems in quantum many-body physics and adapting them to this sort of time series machine learning context. And one of the sort of primary advantages, which you'll come to see, is that it allows us to tackle a whole range of problems under this sort of unified framework. And a lot of existing approaches are sort of developed in isolation to address only some of these problems, like, for example, just focusing on classification or just focusing on time series imputation, which I'll get into later as a problem class. But this approach is one way to sort of tackle all of these different problems within like a consistent framework or probabilistic framework that is enabled by this sort of quantum mechanical interpretation. I would like to emphasize as well, this is a quantum-inspired approach. So these are ideas adapted from quantum mechanics. So there will be lots of analogies being made. So don't take them directly at face value. They're more so just to sort of understand these connections between two different fields. So just... Oh. Okay, so this is just a brief overview. I'll start by talking a little bit about the time series joint distribution and why it's a powerful statistical object for tackling a bunch of these different time series machine learning problems. And then drawing on inspiration from quantum mechanics, we have this quantum many-body problem where these sort of tensor network approaches, like the matrix product state, for example, have been developed to tackle these issues. And then we'll look at how we can sort of use these quantum-inspired approaches and adapt them to time series ML problems by framing them as statistical inference problems. And then I'll kind of try and go pretty quickly over the methodology just because there's a lot of algorithmic details there, which might not be particularly relevant. And I'll show you some cool results that we found applying this. Okay, so starting off, quick look at the time series joint distribution. So here's a quick example where there's only time series of length 3. So we just have 3 points here, ordered in time. We have n observations. So each time series here is a realization of some underlying generative process. It might be like a noisy, trendy sinusoid, for example. And using like a finite number of observations, we want to be able to infer the underlying joint distribution of the generative process responsible for generating these time series. And one way you could think about it in this sort of nice three-dimensional representation is each point here could represent a time series realization or a time series instance. So we have this embedding, and here's like one time series realization, and it corresponds to a point in this space. And then we can model the time series joint distribution. So this is like the probability of observing all three of these values. So this time series sequence generated by this underlying process. And so for a given data class, which here could just be like every possible realization of a time series from a generative model, we have this space and we have these finite observations that we obtain from the system. We almost never have access to all possible realizations. So we have to make some inference about the underlying process from the empirical data that we have. So the goal here with generative modeling is we want to infer this sort of blue distribution from only this finite number of like, we want to call it training instances or observations. And so why do we want to model this joint distribution? Well, there's many different sort of ways you can frame this, but we have a bunch of different time series machine learning problems. You can consider this as different sort of problem classes. Some might be subsets of others, but we have classification here. So distinguishing between two different classes, you might have a joint distribution representing one class of data, maybe a noisy sinusoid with a positive trend, and then like another one with a negative trend sloping down. And we want to be able to distinguish between them. We can formulate this as a sort of statistical inference problem, starting with the joint distribution. Another application might be anomaly detection. So you might have a signal and there's some observation that's unlikely given the past observations of sort of normal or non-anomalous behavior. And we want to infer the likelihood of some new time series given these examples of normal time series from this system. Another particularly important application is time series imputation. So we often see in science and even in industry, there's a lot of sort of situations where sensors might go down and this kind of gives you a sort of gap where there's sort of missing measurements. And in order to do downstream tasks like classification, often a lot of these machine learning models require having access to all the observed values. So we need methods to be able to sort of impute or fill in these missing values, ideally given information from the observed values. So for example, this blue trajectory here. Also forecasting. So given past observations, we might want to predict what the future values might be, particularly important in finance. And another might be synthetic data generation. So actually, once you have access to this joint distribution, sampling from that distribution to generate new time series realizations here, which weren't actually part of the original training set. Okay, so we can think of the joint distribution as a sort of Swiss Army knife for time series analysis. So we have all these different applications stemming from this sort of underlying framework, this probabilistic framework. And so we need methods to be able to sort of estimate this joint distribution from these observations. And so what sort of methods might we resort to when trying to estimate this joint distribution? And some of them you might be familiar with, for example, a kernel density estimate, Gaussian processes for time series data. We also have these sort of deep learning models like normalizing flows, which can sort of take a base density. So you propose a distribution and you sort of, through a series of invertible transformations, you can sort of craft a complex distribution which closely matches your data. The issue with a lot of these approaches is that they don't typically handle high dimensional data very well. So KDE might work well in the, two-dimensional, three-dimensional case. So that might be a time series of length t equals 3. But what happens when we deal with time series with over 100 samples or much longer, thousands of samples? What kind of approaches do we have? And these two on the left here don't do too well in that case. Deep learning might do okay, but they're quite difficult to interpret. They have these black box internals, and they can have complex model architectures. So we need a new way to sort of estimate this joint distribution from data. So another sort of space in which they've dealt with this sort of problem is in quantum many-body physics. And I think the best way to sort of introduce this problem and how they dealt with it is just using a 1D spin chain. So we just have a 1D chain here. Each spin can take a state up or down. And so we have this, say there's n particles in the system. We have a wave function that describes the joint state of all these different particle configurations. So we have a spin chain configuration. Now, classically, in a classical computer, it's very difficult or impossible to store every possible state of this spin chain. You've got 2 to the n possible states for like an n length chain. And so one of the sort of really powerful methods they came up with to be able to handle this problem is and store these sort of coefficients that describe the state of the system in a classical computer is to use something called the matrix product state. So they propose this sort of MPS ansatz, and essentially it's a sort of compression. You're able to compress down these coefficients into a representation that you can then store on a classical computer. And we go from something with 2 to the n amplitudes, if you want to think about it that way. So something that's exponential in the number of sites to something that's now linear in the number of sites here, which is the n. And so one of the assumptions it sort of makes is that if you have this sort of...
Can I just ask a quick question, clarification? So you said that it's difficult to store in the classic computer if each of these things is binary, then it's not a problem, right? It's just if it's a quantum bit.
Sure. Yeah, this is just a simple sort of toy example, but generally we'll have it might be a high dimension, it might be like a d equals 3, d equals 4, and so on, goes up. You could have multiple possible states. So this is just a simple 2-level system to sort of give an introduction, but you can imagine it can get much more complex than that. And you have this sort of full Hilbert space here. And the assumption is that there exists some sort of subspace, they call it the physical corner, where you have these states with low entanglements. And so, for example, low energy states, ground states, and the MPS is able to model these quite well. And it turns out for a lot of applications, this is actually a very useful sort of assumption to make. And so this is a sort of compression that we're making here.
But if n is like 100, 2 to 100 is a big number. 2 probabilities to store.
In a classical computer, yeah. So we go from something that's exponential to something that's linear in the number of sites. I might just breeze through this because this isn't very relevant, but essentially when we see this sort of structure here, I'm not sure if you're too familiar with MPS, but this is called Penrose notation, and it's just a graphical representation of a matrix product state. Each circle represents a sort of either a vector, a matrix, or a tensor, depending on the number of dangling legs you have. And so we can represent our MPS in this way. There's two hyperparameters of interest that are quite important. We have this chi value, which is called the bond dimension, and you can think about that as capturing the entanglement between these spins in particles if you want to think about the quantum representation. And you also have this d value, which is the physical dimension, and that's a dimension of this this open dangling leg here, and we'll probably go into more detail about what that means in the time series context later. We can also have a product state, which is a minimally entangled MPS. So there's a bond dimension. You can think about that as having a bond dimension of 1. And then we can represent operations like inner products using this graphical notation. And so sort of recapping on what we said before, if we have a bunch of spin chains, we can define like a joint distribution over all possible spin chain configurations. Very difficult to store in a computer. So this is like a high-rank tensor that represents all possible coefficients for our many-body system. And then we have this low-rank approximation enabled by the MPS. And we can now store this in our computer. And it gives us the sort of traction, I guess, to work with these representations and do experiments and analyze them on a classical computer, whereas that might not necessarily be the case with the full uncompressed representation. And so MPS, as Ben sort of touched on before, MPS are a natural fit for time series data. We have this sort of correspondence here between the spin chain configuration, which we can represent as a product state. So each spin can then be encoded, the spin state can be encoded to a vector. And we have this product state, which would be a tensor product of all these different individual vectors here. And on the right, we have a time series instance. And you can think about that as each time series value here, you can map onto a vector, which represents the state at that particular time point t, and x here would be like the amplitude, so the signal that we're measuring. And so the idea is we're going to try and adapt these approaches, which are developed for quantum many-body physics, to time series analysis. And so this was taken from the preprint. This is like a sort of high-level summarizing the analogy between both sort of time series analysis and quantum many-body physics. So once again, we have the spin chain. We can have for our many different possible configurations an entangled many-body wave function. And we have like the space of all possible spin chains. And then likewise, we can think of having a single time series instance. We can also have the space of all possible time series being generated by some underlying process, and that defines some distribution. And so there's sort of correspondence here.
Yeah, can I ask you to go back one slide?
Yeah.
So the correspondence here, that's the part that I didn't actually understand.
So, yeah. On the left, we have particles essentially that are arranged in space. So we have our MPS would capture the spatial correlations. You can think about the entanglement between the particles. So that would be the case, the quantum sort of side of things. And then the time series analysis, we have 1D data structure as well. We have measurements ordered sequentially in time. And the idea is that the MPS will capture, instead of spatial correlations, we have temporal correlations.
So wait, maybe one slide back or something. When there is each of this A thing has this, something like that. When you had the this kind of state, probably implying the correlation or entanglement. The next slide doesn't assume that, right?
Yeah, this is a product state. So here we're looking at an MPS. So this would be our model that represents essentially, well, a variation of it can represent the joint distribution. Here we're looking at a single time series instance, which we're representing as a product state with zero entanglement.
So that translates into time series where each time point is independent or from each other, or?
It's through the training process, it will learn the correlations between time points, but you start off with this minimally entangled, zero entanglement state. It might become more clear when I go through the training procedure.
Okay. Okay.
Okay. And so here's a sort of high level overview of the approach. So this will sort of mimic the subsequent steps of the methodology, but we start with looking at ways to sort of map. So we have a continuous value time series. So each value, the value at each time point is a continuous value. We need a way to sort of map that into a representation that's compatible with this discrete quantum approach. So we use different time series encodings. We primarily consider Legendre feature map, and you can consider, say you take a point x, a continuous time series value x equals 0.3. We project that onto our bases, and we can select how many bases we want. So we make a finite basis approximation. And this allows us to take our continuous value and map that into a discrete representation here. And this is like one of the places where the approximation comes in. We're trying to represent a continuous value with this sort of discrete vector here. And then we look at how can we train it, which I'll go into more depth in a bit. And then sort of the two key applications, once we have this sort of MPS approximation of the joint distribution, how can we use that to then tackle problems such as imputation and classification? And so one example of how we can encode these values into quantum states is just to consider a simple binary case. So we have some x tilde value, which is a threshold that we can set. And any value that falls below that would just get mapped to a spin down state on a particle. And any value above that would just get mapped to a spin up. And so this is what we call our feature map. This is just the mapping from our continuous time series value to this discrete representation. You can think about this as a 0 and a 1 and vice versa. Okay, I won't dwell on this, but you can sort of extrapolating from the sort of 2-level system, we can then go to some arbitrary dimension. We call this D. So this is just the number of basis functions we choose in our feature map. And so how can we train our MPS? So we have our data distribution here. So this is a little illustration showing all these time series that we observe from some system. Say it's like a noisy, trendy sinusoid, and this defines some distribution, some joint time series distribution. This is the empirical data we're working with. And our goal is to approximate this using our MPS. And so we have the two distributions here. So the white curve, the white distribution would be our data distribution, and the blue is the MPS approximated distribution. And so we follow a sort of, it's called a sweeping optimization approach. You can think about it as a sort of a local optimization approach as opposed to a global. So instead of just treating the MPS at all the sort of, you can think about the A's as the weights. We don't tune them all in one go. We use this sort of sweeping approach. We start with randomized values. So, you know, you might start with, it's very likely you have a very bad approximation of the joint distribution, just initializing with random weights. And we do this sweeping process where we go up and down the MPS, optimizing 2 sites at a time. So we sort of fine tune these values to go in the direction defined by the gradient descent. And each time we do this sweep, we should see the 2 distributions starting to converge. And the way we measure the convergence of the 2 distributions is using this Kullback-Leibler divergence, which is this information theoretic measure that tells us something about the discrepancy between 2 distributions. So if they're well aligned, we should see that the Kullback-Leibler divergence approaches 0. And in the case that they're exactly identical, they should go to 0. And so we do this sweeping approach many times, up and down the MPS, fine-tuning these values until we either converge, the Kullback-Leibler divergence no longer changes and we decide to stop, or we use a validation loss or something similar. So very much a typical machine learning approach here. And so once we have our MPS,
I'm still not following. Can you go back, slide back? Yeah. So in each sweep, are you trying to change this vertical thing and also horizontal thing at the same time?
When you say horizontal, vertical, what
like
do you?
This one.
Yeah. Oh, right. Yeah. So the D value, so this physical dimension here, this is the dimension of it is fixed, but the values themselves change. You can think about it as a tensor or a matrix. You have a bunch of values in a matrix, and you're just fine tuning these weights. If you want to think about it as weights, but so the D value is fixed. The chi value though can change. So it's an adaptive approach. And one of the sort of advantages of having this local optimization is without getting into too much detail, you sort of merge two neighboring sites into a higher ranked tensor. You optimize that tensor and then you decompose it using a singular value decomposition. And by doing this singular value decomposition, you can choose a cutoff at which you want to make sort of an approximation, and it lets you sort of compress down essentially. So you might start off with a high chi value, and over subsequent sweeps, that value might drop as you sort of truncate small singular values.
Okay, so maybe I don't fully understand, but this horizontal thing is basically the matrix or tensor optimization.
Yeah, yeah.
And then what's this vertical thing?
This is called
S1
dimension.
and then A1?
In terms of the encoding, if you want to think about it this way, so this is just the essentially the D value, which is the number of finite bases you use in your encoding. If I go back, you might see on this here. So say D was 3, you use 3 finite bases. So you're projecting your X equals 0.3 value, for example, onto 3 bases, which is a pretty, in practice, it might be a pretty poor approximation. And the idea is that if you go to higher and higher D, you get a better approximation of this continuous time series value. There's a sort of these two competing hyperparameters. You've got the chi, the bond dimension, which kind of controls the model complexity, and then you've got this D value, which sort of controls the sort of approximation you're making in encoding these values into a discrete representation.
Okay. I think I start to understand. So given the observed value, you are trying to assign some kind of estimate of the D value to approximate or represent the value in your kind of model.
Yeah. So later on, we'll get to it, but you'll see as you sort of fine tune this D value going the other way. So we're sort of, when we're doing imputation and we want to reconstruct these sort of continuous values, that's where the D value starts to become very important. So we have a very poor approximation of our original data, continuous data. When we try to sort of project back into the original continuous domain, it's difficult to resolve to a high degree of resolution these different values and sort of discriminate. So you get more noisier, rougher sort of trajectories.
I see.
Yeah.
Roughly. Okay. But what this part is?
Yeah. Oh, yeah. So this is, so if you just consider the top half, this is the MPS that we have. Essentially, in the math comes out that if you want to represent the joint distribution, you just take 2 copies of the MPS. You take its original self and then its complex conjugate self, and you sort of, this represents the joint distribution essentially. So this data object here would represent this blue joint distribution here. And this is a low dimensional representation. Obviously, the real joint distribution is going to be much higher dimension. This is just for visual purposes.
Okay. Well, I don't really understand, but go ahead. Yeah.
Okay. So once we have our trained MPS, some of the things we can do, we can classify. So you train one joint distribution to represent class A, for example. So it has some distinct behavior. Class B has some distinct behavior. We have 2 MPSs. You can think about it this way. One MPS representing class A, one MPS representing class B. And then given a new time series, we can essentially do this overlap operation and compute the probability amplitude of this sort of unlabeled time series under each of these different classes. And if we square it, we can get the probability density, the probability, and then we can just take the class that gives you the higher probability of observing this instance. And then another thing we can do is imputation. So for example, we have our trained MPS. So once again, we have this data structure, which represents a joint distribution. We can then condition it. So in this example, we have this green curve represents the observation. So this is what we observe. And this red sort of box just is sort of these time series that are unobserved, say the sensor goes down. We can then condition the distribution by essentially measuring the known values. And then, so down here, we have our conditional distribution. So sort of measuring, say, sites that aren't there. This is the conditional distribution given by after having measured this sort of green curve here. So given these observations, we want to sample from the distribution conditioned on those. And we can do that to essentially infer the missing values. Okay, I won't, this is sort of like the algorithmic details. I'll kind of just, in the interest of time, I'll kind of just skim over these, but this is the sort of way that you can sort of do this conditioning approach for imputation. And so we'll start with a synthetic example. So here we have a controlled setting. We're considering noisy, trendy sinusoids. So we just have these sinusoids, randomized phase, 3 possible periods. So you have these 3 values, and then there's also 3 possible trends. It can either go up, it can have no trend, or it can go down. And so we're generating lots of these examples, and we're throwing on a little bit of observation noise on top of that with some sort of strength, eta here. And so we have this data distribution, some complex distribution, which represents this these noisy, trendy sinusoids with these possible trends and phases. And so our goal here is that given a new unseen time series data, we'd like to be able to sort of infer artificially corrupted examples of this time series. So just as a sort of summary of what we do here, we take our unseen time series, we generate it from the same underlying model. We then artificially corrupt it, given some percentage data missing. So say, for example, we want to remove 5% of the data, a particularly easy case. We take it, we artificially corrupt it, we remove those values, and then we use our MPS to try and impute those values. And we use a mean absolute error to quantify the error between our imputation and the ground truth, which we have access to because we generated this data. And so we looked at a few different benchmarks to sort of compare against. And one of them is this nearest neighbor imputation approach, which essentially just looks at examples in the training set and finds the one with the closest, the one with the smallest Euclidean distance to the observed data, and then sort of fills it in. You can think about it in that way. And then we had a few sort of deep learning state-of-the-art approaches as well. And so here's some examples. On the left here, we have a plot of the error at different percentages of missing data. So each time we're removing a larger and larger window of values, and we're trying to impute them, and we're computing the error here. And so lower is better. And the one nearest neighbor baseline, we can see in gray, and then the MPS, we're looking at 3 different values of this parameter chi. And once again, we can think about this as the sort of model complexity or the model expressibility. And so a larger chi value means more model parameters. It's able to sort of fit to much more complex distributions. And we're considering we'll just consider the low noise case, so the hatched or checkered boxes. And we can see that generally, as we decrease the percentage of data missing, the error goes down, which is what we might expect because we have more observations off of which to sort of infer the missing values. And on the right, we have some examples of what these imputations actually look like. So the dark sort of shaded boxes are, this is what we observe. So we feed into the MPS this data here and here. So we give it the start and the end. And then we essentially let it impute the values in between. And so the red curve is the MPS imputed values, and underneath you can see in the white is the ground truth. So this is the values that we actually just artificially removed, and so we can get a sense of what this sort of looks like in practice. And then down here we have another example where instead of just sort of filling in this big contiguous block in the middle, we're actually sort of feeding in lots of different sort of segments or blocks and sort of filling in between. And so another cool thing that we can do with this is we can actually sample trajectories. So instead of just imputing in like one trajectory in the previous example, we can actually condition it on, say, the first 2 points, and then we can just let it sample many possible realizations from the conditional distribution. And so here we're looking at multiple different trajectories. So we start at site 3 after observing site 1 and 2, and we sample site 3 from the conditional distribution, and then we move to site 4, and that value would be determined by values 1, 2, and 3, and then so on and so forth. So each time we're sampling a new value, we're measuring it to update the conditional distribution, and then we're sampling the next value and so on. So each point is conditional on each previous point. And So that's the 2-point conditioning case. We can see that there's lots of different phases. It doesn't have enough information to pin down the phase of the observation. But what happens if we feed in 50 points? So we observe the first 50 points, and then we let the MPS try and predict essentially the next 50. And we can see here that the phases are much more well constrained because we have access to a lot more information on which to condition our joint distribution. Okay, this is essentially the same as the previous example, except it's a slightly more complex distribution. So here we're considering 3 possible trends. It can go, up, down, or sort of no trend, so it's flat, stationary. And once again, the MPS performs pretty well. Won't dwell too much on this part, just more so the trajectories you can see on the right here. So we can see what happens when we feed in some of these observed points. So the shaded boxes are what we observe, and then we have these sort of MPS imputations. And you can see it compellingly sort of fills in the missing values quite well compared to the ground truth here, which is in white. Okay, and then sampling. So in this case here, we're actually not conditioning on any points. So rather than observing the first 3 points, we're just sampling from the first site onwards. So we're sampling the first site from the unconditioned distribution, and then the next site would then come from the distribution condition on the first site. And so we do this sequentially from site 0 all the way through to 100. And so we can see, once again, this complex distribution, we have 3 possible trends, 3 possible periods, and you can kind of see that is what is being produced by the MPS. We have 3 distinct sort of bands here corresponding to the different trends. Okay, and then so that was the synthetic examples. Now looking at some real world applications. So for example, we might have in astronomy Kepler light curves. So stellar measurements as a function of time. Often there's sort of the case where you have sensor downtime. The satellites might turn around to relay data back to the Earth, and during that period, you have a sort of blackout where you're not observing these light curves. And so one potential use of these imputation methods is to fill in those missing periods of data. Another one might be ECG, so human recordings for heart rate measurements. As an example, and then also we have power demand, which is a sort of over a 24-hour period, the power demand of a small city, and that's another like sort of energy application we might be interested in imputing data if sensor measurements go down. And so here we have an example comparing it to some of these state-of-the-art approaches. So MPS here is in red, and we can see it performs quite well compared to some of these other approaches. Once again, lower is better, so smaller error. And once again, as we expect, when we go to smaller percentage of data missing, the error drops. But we can see across the board, it's generally doing quite well. One nearest neighbor is also doing quite well, which is something we found pretty consistently, especially when we have a densely sampled training data set where there's lots of close matches that we can sort of match to and impute. We find that one nearest neighbor also does quite well. And on the right here, once again, we have some examples of what these imputations look like. So these are the observations. We feed in the first, say, 8 points, and then the last few there, a couple hours. And we have this nearest neighbor in orange. So this is what the closest fit from the training set is. And we also have the ground truth in white, and the MPS tracks pretty closely to this ground truth. And there's a second example there. And now looking at some of the trajectories for Italy power demand, so conditioning on the first 5 hours in this case, we can see that there's quite a lot of diversity. So there's many possibilities given only the first couple of values. But if we then ramp that up to 10-point conditioning, so we'd have access to the first 10 hours, we can actually see that the trajectories are much more constrained. So there's fewer possibilities of the different trajectories that time series can take. And so this is looking at the ECG data set. Once again, pretty good performance across the board for MPS in red. Nearest neighbor also tracks very closely. And as we sort of decrease the percentage of data missing, the error goes down. And so these are some examples of the imputations. And you can see that MPS performs quite well in this case as well. It sort of is able to reconstruct this QRS complex, which is a distinguishing feature of the ECG signals. And so here's some more trajectories. This is for ECG. And yeah, what's pretty cool is that it's able to capture this secondary T wave in the ECG as well, which is kind of neat. And another way we might be able to sort of visualize what the MPS is learning is to look at this. This is essentially a time marginalized kernel density estimate of the time series. So you can imagine at each time point, we take a slice and we look at, for the entire training distribution, we want to look at the distribution of amplitudes at that time point. So, you know, this ECG, there might be a high density of time series values near x equals 0. And then we're kind of like going through and looking at different time slices. So this gives us an idea of the sort of the distribution of the training data. And ideally, if our MPS is capturing this underlying distribution of the training set, it should look quite similar in terms of the densities. And so this is at the bottom here, what the MPS is capturing. So here we're sampling from the MPS and we're comparing these artificial synthetic trajectories to the real world ones. And I guess the sort of key takeaways is that we capture these important sort of temporal structures like this initial peak, the QRS complex. We have this sort of dip, and then we also have some, you can also kind of make out this T wave here at the end of the ECG recording as well. So that that's what's happening there. And we can also see that the densities generally correspond to the same sort of regions of X. So this gives sort of
maybe this is a thing that you can probably address after the break in more detail, but I really don't understand how it's possible that so here you are looking at only the initial bits of the thing as a training, right?
No,
Here.
so in this example.
Oh.
So for training the MPS, we're giving it access to the full joint distribution. So it sees all time series of length. Yeah. So here it's 96. There'll be 96 samples, so 96 time series values.
Okay.
And so that it's capturing the full joint distribution, or an approximation of the full joint distribution. But then we're conditioning it on with an unseen example on the first. Yeah. So it's using information from the joint to fill in these values.
I see.
Yeah.
That was really strange to me, but okay, now I understand it. Okay.
Cool. And so here's an example where in the previous examples where we're artificially removing these values because we have a ground truth, so we can compare the imputations. But with this astronomy data set, there is actual censored downtime. So we have periods where there's no ground truth. And so while we can't compute sort of errors, we can sort of inspect, at least qualitatively, some of these imputations to see if they make sense given the sort of surrounding context. So these are some examples from 4 different classes of star system. We have this RR Lyrae variable system. We have this contact eclipsing binary, non-variable, and gamma Doradus. And we're comparing MPS time, which is our MPS-based approach, to a nearest neighbor baseline. And here you can probably see that the nearest neighbor does quite well. And we'd expect this for these highly periodic systems. We have this sort of repeating pattern. And so typically, if you have a densely sampled training set, you'll find something that's a very close match. And so that's why nearest neighbor here performs quite well. And also in this system, not so much the case with this gamma Doradus variable system where we have this more complex nonlinear behavior going on. And so kind of riffing off the slide that I had before with comparing the training distribution to the MPS, here's a comparison across all 3 of these real-world data sets. So this was the ECG. We can also see this power demand data set. So on the bottom, we have the MPS learned distribution, and on the top, we have the power demand train distribution. So this is what the MPS is seeing. This is the all possible training examples from this data set. And then we're sampling from the MPS to generate these new completely synthetic, unseen examples. here we're looking at a relative density. So we're able to make comparisons between the training distribution and the learned distribution, just to get a sense of where we have these high density regions in the true ground truth data and in the synthetic ones to see the correspondence. And we can see it does quite well. There are a few cases where perhaps it doesn't capture as much diversity, but this is a very small data set, so it doesn't have a lot of training examples. And we also have this noisy, trendy sinusoid data set from before with 3 possible trends. And you can see that that sort of results in this complex structure here with 3 distinct bands corresponding to the different trends. And we can see that the MPS is able to sort of reconstruct that band-like structure. We also see a little bit of noise here because our trajectories, because of this, in part because of this finite basis approximation, we just generally get noisier sort of trajectories being generated, but that can be in part mitigated by increasing our finite basis approximation, by increasing that D value to make it larger, of course, at the expense of computational complexity.
Joshua, maybe if it's possible to go to the kind of general conclusion and then go into this kind of details after the break, that would be appreciated.
Sure.
Yeah, because it's becoming a bit too, detailed.
No worries. So just quickly, some future directions. We can look at using translationally invariant MPS. So the idea is we have this inductive bias where we can make, instead of allowing these different tensors to take different values, we can add some constraints on which values they can take, and we can have a unit cell. So we have repeating patterns of tensors, and this might give us some advantage in forecasting and other in stationary time series analysis problems. Okay. So we have an MPS time Julia package if you want to play around with this to get a sense of what it's about. A special thanks to my colleague Hugo, who spent countless hours developing this amazing package with lots of documentation if you want to go through the specifics. And he's optimized it so much that you can run it on your laptop or desktop computer, which is very nice. So you can run that locally and it's very accessible. So if you're interested, just visit the GitHub repository that's in the link there. And so in summary, the time series joint distribution is a powerhouse for time series analysis. We can sort of formulate a lot of these different problems in a framework where we can, starting with the joint distribution, tackle these problems. Typically, it's difficult to represent or approximate this joint distribution because of its high dimensionality. But using methods from quantum many-body physics, we can tackle this time series joint distribution problem, and it gives us a way to sort of address a lot of these time series analysis problems in the real world. And yeah, I'll leave it at that. If you want to check out the preprint, there's a QR code there.